Good morning, ladies and gentlemen. Thank you so much for being here today. My name is Rabih Solh. I'm the Product and Business Development Manager at George Fisher. In my today's presentation, and within the window of 20 minutes given, I'll try as much as possible to walk you through the different flow solutions George Fisher is proposing to overcome the current and the future challenges foreseen to face our different cooling systems within the data center. But before jumping into conclusions and start talking about solutions, let us have a look into what is the real problem, what's the real picture of our different cooling systems within the data center. And to start with, we'll start with a simpler system, which is the chilled water system. At the moment, carbon steel is the most adopted solution, the most trusted solution. From a technical perspective and from mechanical properties to meet the pressure and temperature, indeed, steel is a strong material. However, checking the other KPIs, we find that this solution fails, unfortunately, in every other single aspect, from corrosion resistance in harsh environments such as ours. And despite of all the latest technologies in corrosion inhibition, performed here by our neighbor next door in Abu Dhabi, the oil and gas industry, who struggled a lot with water corrosion. And every single solution has been tried to prolong the lifetime of carbon steel. Yes, you can prolong it a bit. However, corrosion is still a destiny that cannot be avoided. Moving to the thermal losses, and we can hear speakers, everyone is talking about efficiencies, about power utilization efficiencies, about cooling efficiencies as part of the burden on power and limiting the full industry from development. Metals are conductive for heat and for electricity. And carbon steel is one of the most conductive material for heat. So it doesn't look to be the best fit when it comes to thermal insulation and thermal losses. Weight is a disadvantage of steel. However, nowadays, it's not anymore just a disadvantage. We've been hearing market insights, and we know how many projects in this area has been stopped for months because of the heavy weight of carbon steel and the existing steel structure, despite how complex it is, not being able to carry the weight. We know about the projects that stopped for months because of this issue. And with carbon steel, you will face it a lot. So this is becoming more than this advantage, a bottleneck limiting the industry from developing. The ease and speed of installation is definitely another pain point. The supply chain of steel is complicated, as we know. It's not fully in country. We don't have full control on it. And with the complex jointing solutions, such as the hot welding, the process is becoming more and more complicated. The hydraulic efficiency, the roughness of steel, even the seamless one, will add the complication. But the operation reliability, which is the big topic, meeting the 5 nines, 99.999 uptime, is looking to be not attainable using the old tools, such as carbon steel. And since we are all here talking about sustainability somehow, so when it comes to your carbon debt, the carbon debt of your piping scope, expect a big environmental bill and a big bill to be neutralized. From carbon steel, I'll move quickly to the direct liquid cooling, where it's debatable, as we heard from the panelists, what is the rack capacity to expect. However, we're talking in the range between 80 kilowatt to 100, 140 kilowatt. And it's increasing, and this trend will tell us that DLC will be seen more often and it will be deployed massively. However, this technology will be faced by technology as well, as the latest cold plate design is showing that the microchannels are shrinking from 50 micrometer to 25 micrometer and somehow standardized at the moment. However, this trend is reducing, and we are foreseeing a further reduction to 15 to 20 micrometer. This development and this change will put challenges on the quality of our technical water, as the size of the contamination is now limited to 15 to 20 micrometer. This contamination resulted from welding, resulted from scaling, resulted from corrosion, and yes, stainless steel can corrode, can block these channels and can interrupt the cooling process. Deionized water showed a serious candidate to partially address the problem. So with deionized water, the scaling problem is somehow eliminated. However, the existing stainless steel system is not supported to accommodate new technologies. Deionized water, by default, it will tend to go back to its normal watery state by the leaching process, by leaching minerals and ions from the wall of the stainless steel pipe. And with time, the quality of the deionized water will be degraded, as well as the quality of the stainless steel wall. So we will enter into an endless loop, and the existing stainless steel, in short, is not promising in this regard. So the million or the billion-dollar question, since we're talking about a big industry here, is can we still use the inherited tools to face today's and tomorrow's problems? Obviously, the answer tends to be no. What we're proposing, as you expected, we are proposing to replace the metallic solutions by non-metallic ones, and polymers in specific. Same like the metallic world, where we have segregation and distribution of roles, we have also different horses for different courses. Starting with the chilled water system, the polymer found the best fit for such application is the high-density polyethylene for different reasons. First, its ability to meet pressure and temperature. It's found in different pressure rating, 10 bar, 16 bar, 20 bar, way more than the industry needs, the application needs. In terms of temperature resistance, it's up to 60 degrees. In terms of the commercial aspect, which is very important, it's quite comparable with the carbon steel, so this upgrade to HDPE won't be that costly. In terms of variety of offering, from jointing system, can be in butt fusion, electrofusion, pre or post-insulated. But the characteristics I'm going to discuss here will be to address the pain points listed earlier, from corrosion resistance, knowing that polymers in general and HDPE in specific is inert to water. There's no chemical reaction between the material and the media, so this will guarantee a corrosion resistance, corrosion-free system for life. Way faster, the full supply chain, and we'll see in a minute in a dedicated slide why it's much faster, up to 4 times than carbon steel. It's 80% lighter than carbon steel, and the 80% is derived from what we've seen in terms of design. We will also touch on this topic in a dedicated slide. Given that the material itself is acting as an insulator, polymers are insulators, used as insulators. So by default, it will help in reducing the cooling requirement, the cooling power, and optimize the cooling efficiency. So here we're talking about a better cooling by 30%. Uptime 99.999%. It sounds to be attainable with such solution. Maintenance-free, corrosion-free for over lifetime, so we can have 100% peace of mind. And last but not least, the sustainable factor. With the solution, 60% of the carbon debt of your piping system will be cut. Now, the material selection impact on project timing. Unlike the steel, where its supply chain is complicated, the supply chain for polymer and HDPE in specific, it's 100% localized. From the raw material manufacturer, Borouge being next door, to the final product manufacturer, even to the prefabrication based on Abu Dhabi, so that the modularity or the maximum in-house prefabrication model is feasible. For the portion of the jointing left to be done on site, the selected jointing system is the electrofusion, which is quite simple, quite fast, just to make sure we have minimum involvement from the bonder and minimum expertise requirement. And in terms of speed, it proved to be way faster than the conventional welding system. And when it comes to flushing, this is a different subject. At the time, I have 2 systems, one in HDPE, one in carbon steel, ready to be commissioned from a jointing and installation point of view. I need to do the flushing protocol. In HDPE, it's 1 week requirement for static flushing with simply water, no matter how big is your network. When it comes to carbon steel, we're talking about a strict protocol that involves static and dynamic flushing with water and with chemical, and this protocol can stretch to weeks and months. From the designs we've seen, typical designs we've seen in the region, we're talking about flushing time that range between 8 weeks and 12 weeks. We know time is money, but in this industry, time is a lot of money. So with all these factors combined, we are aiming to cut the milestone of the piping, or the timeline of the piping project, by 4 times. When it comes to weight, we did our study on an actual project here in the area. Unfortunately, we're not allowed to mention names. But just to compare, to understand what's the real impact of weight and how much difference between HDPE and carbon steel. Here, the capacity of the data center we have in our case study is 10 megawatt. And the weight of pipes only was found to be 288 tons in carbon steel. Whereas in case the material selected was HDPE, this weight will reduce up to 61 tons. So here we're talking about a difference of 5 times. The weight of carbon steel is 5 times that of HDPE. And this is only for a 10 megawatt data center. You can scale it up to the 100 to the 200 megawatt, just to understand the amounts of weight, how heavy carbon steel can be, and what could be the impact on this weight on the full ecosystem. How complex will be your steel structure, your concrete foundation. The full ecosystem will be impacted. And this impact can be monetized in terms of cost, can be time, and can be stopping the project, like the cases we've seen. From carbon debt, and as part of our offering, we make sure that to support our customers by the CO2 calculation, the carbon debt of their piping scope. And we did, for the same project, the calculation for the carbon debt. And the results are the following. So in case of carbon steel Schedule 40, the carbon debt of the pipes for a 10 megawatt data center would be in the range of 360, 361 ton of CO2 equivalent. Whereas for HDPE, this number will reduce to 155 ton, which will leave us with a saving of around 206 ton, and in terms of percentage, it will be around 60% of the carbon debt of your piping system. Case studies. Our GF experience at GF spans for around 20 years in this field. And when it comes to case study, a lot of projects to be mentioned or to be reflected, but I selected 3 different projects from the pain points that we discussed earlier, mainly time and CO2. So here we have the first project in Dublin, in Ireland, where the pillar was time. The installation time was supposed to be completed in 6 months. However, in case with carbon steel, it was supposed to drag to 6 months. So with HDPE, we managed to meet the installation time in 6 weeks. The second project in Mexico, the pillar is also time. The installation time was supposed to be shortened by 50%, and with HDPE, this goal was attained. The third project in Singapore, and the pillar in this case was CO2 equivalent to reduce the carbon debt, and by selecting HDPE, 135 ton of CO2 equivalent was saved. Now moving from the chilled water system to the direct liquid cooling to the technical water. As you can see in this photo, we were a bit futuristic, and we saw this era coming a few years back, and we made sure that every component in your technical water network is made of non-metallic. From the distribution lines to the butterfly valves to the quick disconnect valves, which we will see it in a second, to the ITE rack manifold. Starting with the distribution system, we at GF, we have all the polymers. All the polymers fall in our portfolio. And our research team did a great job in finding out what could be the perfect fit for such application. And our research guided us to polypropylene homopolymer to be the perfect fit. for different reasons. First, being able to meet high temperature with the increasing heat loads, we are expecting temperature of the return lines to increase definitely. So the capability of this material pushes the envelope of temperature up to 80 degrees. In terms of pressure, up to 16 bar. In terms of ultra pure water performance, just to be futuristic, and our solution to meet today's demand and tomorrow's demand. We just heard the gentleman saying that we need to design data centers for today and for 2, 3, 5, 10 years from now. So in order to be futuristic, this is the go-to solutions when it comes to ultra pure water suitability. This is the solution adopted by big names in the hydrogen business to carry ultra pure water. And this is not a forgiving business. The minute contamination will drastically reduce the efficiency of the electrolyzer. From resistance to the, thermal distortion and the stiffness and rigidity, this material is rigid, so the supporting span followed for stainless steel won't be much impacted. And the very important feature that's related to the sustainable operation, to the 5 nines, 99.999 uptime. The welding technique, the jointing system of it, which is selected to be infrared. So this solution is zero tolerance solution, zero margin for error. The jointing is done almost automated by machines. The jointing is done by machines, the inspection is done by machines, and after the inspection being done, there is another checkpoint added, which is the weld bead inspection to make sure that there is no room for error. Another element or another part of the solution is the quick disconnect valve, which basically will be connecting the distribution line to the hoses heading to the ITE equipments. And today I'm carrying a sample of this, this valve. This valve is supposed to replace its equivalent from stainless steel. However, it will be more convenient in terms of weight, in terms of functionality. It is, as its name says, it's quick disconnect, so it's made of 2 ball valves that can be easily disconnected. Not now, can be easily disconnected and connected. The valves is full bore, made of premium polymer, which is PVDF. This is the go-to solution when it comes to microelectronic cooling systems. With a smooth inner surface, it will ensure much better flow compared to its alternative from stainless steel. Another equipment will be, and the final element would be the in-rack manifold, which at the moment being done with stainless steel, having a quadratic shape. So this shape of stainless steel ITE rack manifold is leading to the fluid to lose its characteristics. At GF, we went back to basics, and we took it back to its circular shape as a manifold. The material selected for this mission is PVDF, and the advantages are not only the weight reduction, which is at least 50%, being corrosion resistance, but also to serve a very important feature, which is consistent cooling at all server levels. So with a stainless steel quadratic shape, the flow rate at each outlet and each port is not the same, is not maintained, is not consistent. So the cooling is not consistent. And this is simply because of the geometry forced by the material. We did our test to make sure that every single outlet of the ITE rack manifold is having a consistent outlet flow rate to make sure the consistent is uniform across the full rack. In terms of experience, and as you all know, relatively, the solution is still considered emerging. We will see it a lot in the near future, but still considered emerging. Our reference list in this regard is not that long. We have 5 projects currently in Europe between completed and still in progress, and 1 project in the US. However, our research and our proof of concept started a long time back, 3 years back. This is a test bed done in Singapore University, where all these elements, all these components were deployed just to assess its workability and its impact on the different figures. And after 3 years, we started receiving some feedbacks. And the most important one would be on the energy consumption, which we managed to reduce by 25%. Last topic will be engineering. Material selection is definitely a big chunk of the solution. And the solution starts there. However, without a proper engineering, we cannot call it a full solution. The engineering of polymers is not hard, but special. So we need to understand that polymers, they have different behavior from steel. With the proper engineering, we can, yes, call it a full solution. And here, we make sure to support you throughout the full journey, from the initial sketch up to the final design. By defining, we support you in defining what is needed, what are the engineering services that you need to make sure you have no loose ends. So from material selection to the engineering part, to the material fabrication, to the off-site manufacturing, we tighten all the loose ends and we make sure you have a zero-tolerance system. Last, this one, I promise you the last one. As a closing, so as a GF, we do have a 30+ experience in a very critical, mission-critical cooling system, such as the one needed to cool the semiconductors, to cool the microelectronics and semiconductor business, and 20 years of experience in the data center business. This experience is now put at the disposal of the industry, at your disposal here, to hopefully help in addressing the pain points in the cooling systems and hopefully allow the industry to grow without compromise. Ladies and gentlemen, that was my presentation for today. Thanks so much.